Today I'm going to go over the direct methods and visual odometry. I'll go through the very basics of why we want to do visual odometry, following to the difference between feature-based and direct, and then moving on to several state-of-the-art algorithms like semi-dense visual odometry, both Disparity, SVO, and DSO. So just to go over the motivation. So why would we ever want to use visual odometry? So normally when we want odometry on a robot, we would use field odometry. But depending on the environment, that odometry measurement is affected by fields. And so using the visual odometry is usually more accurate than field odometry. And aside from accuracy, it can be used to complement other sensor measurements like GPS, or you can sort of put them together to increase the accuracy. Visual odometry is particularly useful with GPS in our environment. So you can imagine borrowers are flying inside indoor environments where you don't have GPS sort of position measurements. And so visual odometry has four main sort of assumptions. First one being that the image or the environment of which the camera is observing has sufficient illumination. The second one is the dominance of static scenes over objects. Enough texture so that feature-based methods could identify features in the real-world environment, and also sufficient scene overlap between consecutive frames. So the last point is more like you need to have a fast enough camera so that in between two frames you can still observe the same features, so to be able to extract the motion estimates. So over the course, we've sort of already covered some of the feature extraction methods, like stiff sort, brief, and fast. So in a feature-based pipeline, you would have some input images and you would extract features based on the feature extractor you choose. These mostly are sort of corner-based feature extraction methods. Then you would have to do a feature correspondence between frames, and you do a tracking and mapping. And so that's generally how a feature-based VO visual odometry works. Whereas in a direct method, the reason why it's called direct is that we're no longer working with features in the sense of discrete features in the sense of stiff, sharp, and fast. We're working directly in terms of light intensity. We also perform the same tracking and mapping, but instead of minimizing the reprojection error in the feature base, we are now minimizing a photometric error in tracking. And the mapping is also different in both cases, which we'll sort of dive in later. So generally speaking, the pros and cons for the feature-based and direct methods is that feature-based only use components, whereas direct tries to utilize the whole image. The second point is a bit baseball. Feature-based is only faster in terms of the sort of the optimization state, because feature-based has generally a sparser set compared to direct, where you could have a lot more features in a direct method as compared to a feature-based, where it relies heavily on seeing the corners of the scene. Outliers is another thing. Feature-based, you would generally use ransack to remove outlines, whereas direct methods is more difficult because you're basically trying to do a disparity search along the certain line. So it's a bit more harder to reject outliers if they do this image. So before I go directly into direct methods, direct methods actually have a precursor, and that is that when stereo matching. So what I mean by that is that if you have an image, what we want to get is the depth of the object seen, and we do that by having two pairs of images. One has a slight offset compared to the first one, and you would obtain a disparity curve that, like the one on the right. And so, generally speaking, when we do a stereo matching, it's analogous to feature correspondence. So, in feature-based methods, you would do something like a ransack algorithm to do feature correspondence to find inliers in between two images. In direct methods, you would perform something similar, but now you're comparing pixel intensities to say whether they're similar to each other, whether two pixels are the same, one image over the other. So the two most basic matching possible images would be like absolute intensity difference and squared intensity difference. So I is just denoting the intensity pixel value in x and y coordinates on the left image minus the right. The squared intensity difference is just the square of the difference. And so when we do a disparity computation, we're basically trying to look for the same pixel on the second image along the epipolar line, and we could use a algorithm called like a winner-takes-all algorithm, where it traverses along the sort of epipolar line to find the smallest difference in terms of light intensity. And using the winner-takes-all algorithm, its disparity map usually looks very bad. So the actual result is on the right, where it's using the winner-takes-all algorithm, and then the optimal result is sort of in the middle. And to solve this sort of low signal-to-noise ratio, we remedy it by using something called a cost aggregation, where we don't just compare a single pixel, but small patches. So by introducing a window size or patch size of arbitrary size, we are able to sort of calculate the sum of the absolute intensity difference between sort of two images of the two pixels. So with so for example, we're comparing the light intensity of the x and y coordinate compared to the right to the left, and summing them up, and that would be our intensity difference, and we want to basically find difference. So there are other sort of area-based matching costs. So the first two are fairly self-explanatory. The sum of the difference when you square it. The normalized cross correlation is a bit more involving, and that is because it wants to reduce the effects of the lighting conditions on the two sets of images. So if one is brighter than the other, this normalized cross correlation tries to mitigate that effect by taking the mean, subtracting the mean intensity, and doing the difference between light intensities on the right image on that pixel. And so we use a combination of winner takes all and area-based matching. We get slightly better results compared to just using it's better, but there's still a lot of errors. So there are many other problems when you use a patch, sort of a local method, or like an area-based approach. And they mostly assume that the patch has the same constant depth, and it's prone to errors when you have repetitive textures, uniform textures in structures. So this top left-hand corner is an example of when it's struggling with repetitive structures. So it can't really tell depth when you have them. And when you have like thin structures, it's sort of affected by it, so it can't really calculate the amps on depth quite coherently. And so, as a summary to like stereo, when I say cross correlation, it's the combination of like winner takes all with some kind of matching cost function. This could be a sum of absolute difference or some squared differences. The reason why we still use it is because computationally they're still relatively simple, fast, and has low memory requirements in the sense that you don't need additional information except for the disparity function. So I talked a lot about stereo matching. That's because from stereo matching we could, it is monocular VO example, we could imagine that we take two different camera frames, and from that small baseline, be able to emulate stereo matching and work out the depth of the scene based on the two images captured by the monocular camera. And so there's a bit more to it, which I didn't have time to cover, which is inverse depth estimation. So if you want to know more about inverse, why we in the video we use inverse depth, these two papers are sort of like the go-to places to go. But throughout this lecture series, we'll be talking about the inverse depth estimation. So, in terms of what is inverse depth? What is inverse depth? Inverse depth. I can only say that it's just, as names suggest, it's 1 over the depth, and it goes along some of the lines of if the object is really far, you just denote it with depth here instead of things. And so one of the first direct approaches to visual odometry in real time was detail. And, I can only cover it very briefly. And, it uses a monocular camera. It doesn't use the feature extraction required in the feature-based method. And the results show that it has superior tracking performance compared to feature-based. But in order to achieve this, it had to use the GPU to sort of speed up the ultimate those are fast in stereo matching. But in DTAM, they used a global sort of matching method where they sort of take the photometric cost volume into consideration. And that's a very computationally intensive process. I didn't read enough about stereo matching to say how different they are. I can only glance through the cost function methodology in that. So in terms of this delta I, this is trying to calculate the sort of light intensity difference. So this is down to how you want to calculate the difference between light intensity. This could be the sum of absolute difference, as we discussed before. The normalized correlation, cross correlation, and the special bit is that it uses this cost volume data term to basically do this sample inverse. And since this cost function is highly convexly approximated, yeah, I don't know too much about. I don't know enough to sort of dig into the math to say how difficult solving this problem. So the main takeaway is that I just wanted to show that DTAM was perhaps one of the first real-time sort of dense VO that needed work, but it had to use a GPU in order to make it run in real time. And so after DTAM came up, there's something that Engel from Technical University came up with something called the semi-dense visual odometry. So the idea is that instead of tracking every single depth pixel, dense pixel, it tries to use a measure to not track low gradient pixels. So pixels that have a relatively low texture. So for example, on the left is the original image, and then right you see the semi-dense depth where it sort of tries to, it ignores the areas of the image where it has low texture, that gives us information about the edges of the table and things that we would like to care in scene. For example, the computer is quite well covered in terms of that. Whereas key point based, it only concentrates mostly around the key, the monitor, and very few pixels around the table, as opposed to the full sort of dense from a direct, dense direct, or like an RGBD camera, like lens. So it's basically a way to get the best of both worlds in the sense of it captures enough in the scene to do motion estimation. So the key contribution of the semi-dense visual odometry, other than coming up with a good measure of how to select features, dense features in the scene, is that it also comes up with probabilistic methods to estimate the depth three sort of different criteria in which it tries to find the dense features through. The first one is through a geometric disparity error, which is trying to sort of measure the influence of a small gradient difference. So it's a bit hard to see in this image, but the gradient is sort of dark on the left-hand side, and it's parallel with the epipolar line. So these two are the epipolar lines of the two images, and whereas this image is trying to denote that the image gradient goes from the top left to the bottom right-hand corner. So the gradient vector is not parallel with the epipolar line, and by having a different sort of gradient vector as opposed to the epipolar line, we introduce a large sort of disparity error. So that's one form of geometric disparity error caused by gradient vector being different from epipolar line. And the second dense feature goodness criteria is the photometric disparity error. So in terms of a image, if you have like a texture-less scene, and you do a disparity search on texture-less scene, then you would invariably have a really large disparity error, because when you're searching for that same pixel on the second frame, it's really hard to find, and so you don't really know your disparity. So what it's trying to say is that it tries to encourage gradients, large intensity gradients over small image gradients, so that, for example, if you were looking at a table, it's really hard to do an epipolar line search for the same pixel if the image gradient is the same. You would want to favor image gradient, high image gradients like black and white, like the corners of the table, over low image gradient. So that's what it means by photometric disparity error. And the third goodness criteria is that it combines both the geometric and photometric standard deviations to work out a scaling factor alpha. And I didn't quite understand how they sort of used the three combined to obtain goodness measure. But if a takeaway from semi-dense visual odometry paper by Engel is that they come up with a scheme, three different criteria, so that you don't track low gradient pixel. So instead of taking the whole image, you want to focus on dense features that you can observe with confidence. And the second key takeaway is that it introduces a probabilistic depth map representation. So all these depth is represented probabilistically instead of absolute value. So in terms of results, they evaluated on this data set where they wave each other around, and they compared it with 7 is DTAM, and 8 is BTAM, feature-based. In terms of drift, they basically demonstrate that it's comparable to fully dense methods, and it outperforms feature-based algorithms and so on. So that's semi-dense visual odometry.
All right.
Yeah.
So what's an example of a dense feature?
A dense feature. So because it's comparing light intensities, when I say dense feature, it's just basically that they're trying to look for the same pixel from one frame to another. And if they come up, if the cost function is trying to say small sort of light intensity difference, then they say that those two pixels are the same. And so local methods, they do this search by sort of traversing down the epipolar line produced by two. So sort of like by using the epipolar line, it constrains the search space to just. And by using things like cross correlation, when you take.
I was asking for the same semi-dense, and this one the patches and so on, how's what's a dense feature in this sentence?
So there
Is
is
it,
no.
I mean, like, back there were patches, what's the size of the how is a feature determined?
How's the feature determined by the matching? And so what I was saying, like the difference between semi-dense and fully dense in these two pictures is that semi-dense has the 3 goodness criteria, which is represented as sort of, you want to minimize the geometric disparity error, the photometric disparity error, and also the pixel inverse depth error. And the 3 combined, if it gives you a small error, that's what they say is semi-dense feature. So those 3 errors basically try to avoid tracking pixels where it has a low sort of intensity gradient. By low intensity gradient, take the table for example. The table, if you traverse from the left to right, has a low intensity pixel gradient because it's mostly white. And so from a search perspective, it's harder to search for. So pixels are the same along the epipolar line. But you want to avoid wasting time updating depth pixels that are hard to correspond, essentially. But you want to focus on pixels that are easier to correspond because they have a higher gradient, pixel gradient, like the edges of the table, things that sort of jump out in red. So a follow-up paper from the semi-dense visual odometry by the same author. He basically created a SNAP algorithm called large-scale directs, and the 3 major contributions is that it tries to build a large-scale consistent map in real time. It uses the semi-dense direct methods that I just described. Sort of, instead of operating on SE3, it operates on this symmetry, which is basically trying to optimize for the scale in the optimization problem. And so it's basically trying to argue for a sort of explicitly protecting scale drift in the optimization problem. And the last contribution was the probabilistic solution to include noisy depth boundaries. So similar to the previous paper, is trying to come up with a probabilistic method of estimating the depth focus. So the general pipeline is you have the tracking part, the depth estimation part, and also the map optimization part. What is different to sort of the SLAM algorithm that we've seen so far is that Peter, for example, takes keyframes relative to time. So after a certain amount of time, they'll take a new keyframe and use that as a basis for tracking new features. Whereas the LSD SLAM tries to take keyframes based on how far the current frame has deviated from the current keyframe. And instead of optimizing in Sim 3, when we're optimizing for the map, instead of optimizing in Sim 3, we're optimizing in Sim 3 to put that scale value inside the map.
What is Sim 3?
Oh,
What is Sim 3?
Sim 3 is it's a simple transformation with a S internal rotation. It's if I won't say I understand it fully, but
Instead of a rigid body transformation, it's called similarity transformation.
basically,
Yeah.
Yeah, similarity transformation.
where this is the scale SO3 and T is the translation vector. Size 3.
But why would they expect things to scale?
I'm sorry,
Why would they expect things to scale?
Why do they expect it to scale? So,
Because it's all monocular, right?
yeah. So different keyframes have different. I'm just regurgitating what.
So in fact, they have a scale parameter for each keyframe,
Yeah.
right? So they don't actually know depth in meters. They just have a relative depth. And then they try to align all the scales to a consistent scale using a Sim3 optimization in the postgraph.
Yeah, so in terms of the direct tracking, there's not much to it. It's just trying to minimize the photometric error between the keyframe image and sort of current image. But Arun, do you know what's the significance of the sort of projection? Sorry, was that? Do you know what the significance is for the sort of function?
Well, it's because the, it's been a while since I've been paper, but the work we had imagined is because you're looking at the information point.
Yeah.
So you need to take whatever exists in the map, and then to compensate for the fact that you're looking at a different viewpoint, you want to incorporate into the observing.
in terms of the optimization, it uses pretty standard approach in well, relative to the field. Like Gauss uses it, I think very well covered, and it has some regularization goals, like who the statistical goal to basically refine the dense features from coarse to fine. That's more to do with to know more about its property than to know fundamentals of stereometry components. So LSD SLAM basically tries to come up with the inverse F of the original image, as well as the variance of each of the inverse pixel. And again, it uses the goodness measure previously described to obtain the semi-dense features.
So where the variance comes from as well. So where the variance is coming from to goodness.
I'm not sure. So this is the part where I struggle the most about in terms of 73. So aside from minimizing the photometric error squared, there's this term, I think it's the variance of the but in terms of the optimizing for the pose graph, didn't really say much other than this cost function, and they said that they just leave it to G2O to solve it. So in terms of the mapping part, I feel like it's added as a small link. So in terms of results, LSD SLAM has improved upon the previous semi-dense visual odometry quite a bit. So it's now competitive with using the direct LGBT SLAM. So this would be the Connect direct SLAM. That's 40. So you can see that in terms, other than the first data set, the other three is really comparable in terms of square error. So the next paper is SVO by Christian Olsen from Scarabus as well. And the SVO is the contribution is more towards speed over the theoretical side. It's basically trying to demonstrate a novel semi-direct pipeline. Trying to say that you can use semi-dense really fast on mobile processor platform to achieve visual odometry. And the second thing is they try to contribute towards the probabilistic mapping. Supposedly is robust to outlier measurements. And so this diagram actually looks very similar to Peter, where you have a motion estimation thread and the mapping thread. The key, there's one thing that jumps out, and that is, even though SVO tries to work with semi-dense features, it actually uses bundle adjustment at the back end to do map optimization. And so also uses feature extraction, which is unusual because if you use a semi-dense feature, you would expect it to use, you won't expect it to use any feature extraction stage at all, because that's the feature-based it's important to note that the feature correspondence is only used to generate points in the keyframe, let's say, and also initialize the depth deltas, which will be used to feature alignment. So I'll quickly cover the motion estimation aspects. So there's 3 steps. So the first part is the sparse model image alignment, which is similar to the semi-dense video first part, where you basically want to minimize the odometric error to obtain the camera transformation from previous frame to the current frame. So the only thing you're optimizing is for the transformation from the previous frame to the current frame. You're not optimizing for the manual positions. And then the second stage is what they call feature alignment, where you're again minimizing the photometric error of the current image with respect to the previous reference patch or reference keyframes patches. Where A is, so the intensity of the kth frame of the U prime patch minus the reference image keyframes of the same patch. A is the applying warping the length. And the last stage is a post and structure refinement, where you're optimizing for both the transformation and the manual positions as well. So this is a basic projection error bundle adjustment. So I basically made some notes saying that the reason why, so the first part already gives us the transformation between the loss key, it already gives us the motion information in the first stage. So why would you care about the feature alignment, structure, refinement? And the authors basically say that through empirical experiments, is that if you don't do this stack, all 3 at once, then you basically have larger drift errors and it just really doesn't work as well. So in terms of results, they basically flew a quad rotating sort of grid and a figure of 8 sort of manner, and they compared it against beta. And from the plots, you can see that it's relatively, the SVO is relatively close to the ground truth as opposed to beta. And the authors basically compared it against the accurate and fast parameters, where basically both outperform beta in terms of magnitude errors as well as position errors. So it's X, Y, and Z, and
Why?
the plot tends towards 0. So in terms of fast and accurate parameters of SVO, it's very close to 0. It's close to P10 where it's so numerically it's way.
Bit off topic. Why do they not just plot the absolute distance?
Absolute distance. They probably did, but I just think. So this is over time. But they didn't do it. So the last paper on DSO, I actually didn't have time to finish reading it. But there's a main takeaway that previously I've introduced direct, semi, and direct, sorry, dense direct method, and semi-dense direct method. DSO, direct sparse odometry, basically tries to introduce the sparseness to direct method. So in terms of what that means, it's basically that optimization stage, it drops a geometric product. And by doing so, it tries to simplify the Hessian structure when you need to do for optimization. So when we do optimization, we tend to want to have a very predictable Hessian structure. So the sparseness, the Hessian and epsilon's left, then dense Hessian structure would be one on the right. And that's for the time given, I can only read up to this point. And so to finish off the presentation, I guess this is the discussion part. So based on like how direct methods have evolved, does this mean that front end don't DSO with sparse direct method? It's like, can we improve on it? Other things is like, is it realistic to aim for a front end VO or SNAP system that is capable of performing all the illuminated environments and textures? No camera frame rate environments points out gold visual.
So they are sort of insisting on using a single camera.
Yes.
So, because there's a problem of depth estimation of maximum of the constitution. So you are sort of solving two problems at the same time. But if you have a stereo camera, you get the depth from the stereo.
Yes.
So you should only solve the tracking problem.
Yes.
That
But,
would probably be easier to get the result.
so isn't there a reason why we don't use do stereo? Because like, isn't there like a trade-off between precision and accuracy? Stereo cameras. So trade-off between precision and accuracy. So I mean that's something that I read somewhere. Because it doesn't make sense that if you have a stereo setup, why don't we just use that to get depth objects?
So the depth estimation for stereo only works well relative to whatever baseline you're operating to. So a rough rule of thumb is like 5 to 8 times baseline is where you can get good depth estimation. So the issue is for autonomous driving, you look at the baseline of the car. So if the baseline between two cameras is maybe 1 meter, that means you can only really do good depth estimation up to say 5 meters, 5 to 8 meters. But often features that we're tracking are much farther. So to be able to get good depth to those features, you can't simply just rely on doing pure stereo depth estimation. Yeah.
And also when you have those amplitude close, then you don't work for low speed. And if it's close and you're moving fast, you're not getting the consecutive. Like you don't get super fast.
But yeah, either a fast scanner or
And then just use, want to take just some close features to initialize, or like take your depth, and then you would know.
some close features.
Like if you start off and you see some features that are less than 5 meters away, that'd be enough to get a depth estimate, and then you can continue using it even if the later features are farther.
Yeah, you can continue using it, but then it's as you get farther away. So if you're doing like what ends up happening if you're doing something the relative distance between your keyframes to the features that you're trying to do the estimation of, the feature depth, often are they're quite far away relative to your you continue to initialize the one to get if you continue to add measures because you're getting farther away, your baseline that's getting larger. And you could either end up having rooms that and it would you might not be able to actually track.
Actually, yeah, that's true.
So to do that kind of estimation, either you have a baseline stereo system, or you get baselines over keyframes that requires that you actually have to track that over the
So I guess the premise why this works is because between the two measurements, use the distance that you travel as sort of the way.
Exactly.
You get much farther than.
Yeah, so that's why you do it. Your baseline comes from using previous images that were that snapshot.
Yeah.
So in terms of so is it solved?
Look, the thing is even depth, right? You're looking, the features are they're coming from gradient. So if you look at how even a feature extraction system works, they're still also doing image gradient to try to find stable marks. Because a simple Harris function is looking for where you have high X and Y distance, right? It's just that that's more of an abstraction whereas the direct method is actually operating this line part of the VO part of one layer lower. So instead of going to the full abstraction of these stable, it's looking at these gradient parts. So I don't think if you were to try to do this in a snow environment where there are no then it would work. In that case, I think any visual system would fail because there's no visual information. You're essentially looking at a white or a completely textureless image. So to solve that, that's where actually a lot of the motivation for something like Visual Odometry comes from. So if you have the ability to move the camera, you can come up with a policy that would be able to select a viewpoint that maintains the location. This would come in the form of either trying to find the highest gradient parts of the images, depending on how you can actuate the camera, or if there's lots of image gradient or high gradient information already, we've been trying to select the best part of that, right? right? So you can either do this on the front end or the back end. What I think is interesting to discuss is on the front end, a lot of the front end features, it's really depending on parameter selection and feature, like parameter selection. So you could really put your front end work really well indoors. If you go outdoors, those parameters might not work so well. You can experience it. So I think what would be a really neat thing to try is if we could come up with a way to do an automated. So this would then allow us to say operate indoors, and then on both sides we have some kind of system to learn how to modify the parameters such that you're able to do better stuff. So the thing is, so this would be actually a really neat crossover between classical design methods and deep learning. So we can use the deep learning methods that start being on-the-fly parameter tuning, because those kind of hyperparameter optimizations are for deep learning.
Agreed. And I think I can't quite hear that well, the discussion, unfortunately. I would be really fascinated to be in the room. But I just wanted to add that the whole information gathering aspect, right? The idea that we're trying to quantify what we're going to most benefit from in the scene in terms of localization, and then use that knowledge before we do VO to select or to navigate or to drive the gimbaled camera or the vehicle in such a way that we stay, that we perform optimally. I think that's huge. And that same assessment, that same understanding of the information content of images applies to what Arun was just talking about switching between different environments, right? So, if we can understand the connections between what's available to us, like what the value is of the information we're collecting to our localization, and put that on a stronger footing, then all this sort of trial and error of, well, this method seems to work better for this data set. We can actually, analytically assess it and understand what's driving it. So that's why I'm so curious about the sensitivity and degeneracy that we've been talking about, and then continuing our ideas around active as well. Adding the learning aspect or the adaptation aspect is even more interesting, but I feel like that will get easy as soon as you understand the content of the information in your collected data.
But to play devil's advocate, if you were to try to solve this parameter tuning using a deep learning method, right? Is the appeal of that approach like that possibly that we don't necessarily need to understand everything? We don't need to understand the information content, but just give it examples of situations where certain parameters operate well in certain environments, and then it could attempt to try to learn how to modify those parameters.
Yeah, certainly. You can try to learn it instead of trying to understand it. Yeah, for sure. And probably we have to try both, right? Probably we have. So, yeah, and we've looked, there's a long history of this information theoretic measures, right? So it is pretty well investigated, and nobody uses it because it seems to not quite work, right? So it could be we're barking up the wrong tree there for sure. In which case you might, if there's some repetition to it or some, structure to it that we just don't understand, then you could learn it in theory, right? But how do you know you've done enough environments, or how, I guess maybe if you do everything in an online manner, you still need to understand what to assess, right? So, yeah, I'm not sure. So what's our goal with Gimbal VO? Do we have an answer for that?
I gave a brief, at least my thoughts, for trying to use the gimbal as active localization.
Yeah.
So trying to get away with the situation you're talking about, right? Where if you're static camera staring at a white patch of snow, the snowbank, that's not adding much for your localization system.
Yeah, and it's trying to exploit the concept or the notion of attention, right? Like this idea that, if you look at the way we observe the environment and what we focus our attention on, right, that has a huge impact on how we move through the environment, and is probably extremely computationally efficient. And I think we can do the same thing with our gimbaled systems. If we know what to focus on, we know what's giving us the most value for what we're trying to do, then we can maximally exploit the use of the gimbal and minimize the amount of computation required, right, to do the same task or to meet some minimum standard. That's my hope, at least.
Yeah, so it'd be interesting to see whether we can, because I guess the idea in terms of trying to correlate it to human vision would be we're able to move our eye really rapidly with like selective coordinates, but somehow from there we can kind of paint a picture of what's going on. So if we just have one lower resolution gimbal cam, sorry, high resolution gimbal cam, we can stitch together a better understanding of high localization, but not necessarily relying on having multiple cameras with 360 field of view overlap just to ensure that we get this prevents feature starvation and all these other things that are the main benefits that we gain from using these multi-cam clusters.
Yep.
So I have just a radical different idea. So when I'm driving, it's not like the road is never a perfect circle, right? Every little stretch of road is somewhat characteristic. Just looking at the lines on the road, like every curvature, right? The curvature of the lines in every, let's say even on the ring road, you can probably determine high accuracy or position on the ring road just by looking at the characteristic curvature of the road, of the lines, right? So has anybody sort of explored using this visual odometry, but in conjunction with having something like a lanelet model, where you only have the left and right boundary of the road, and just basically using the camera to only focus to try to find the characteristic and not with the lanelets.
Yeah, I think that's basically just lane visualization.
Lane visualization.
Yeah, I think that is quite a bit of work. It's very, like it'll do a bit.
It should be simple, right? When you can see the line.
When you can see it. But it becomes more, I mean, that's a very, for the autonomous driving stuff, right? It's more of I'd see more of a niche use case for when you're just driving on a highway. You have a lane on one side and on the other side. But I guess even when you're driving in the city, you have the same.
Well, on the highway, no, because like usually you have like perfectly stretched, like it's perfectly straight, and then it doesn't give you any information about it. Like I see those, characteristics. Like every single corner is sort of different than any other corner, right? And because we are going to drive in a geofenced area, that's what we're looking at, right? How characteristic those lanes are.
Yeah. I mean, one of the issues then is that you're kind of, I see the trade-off being you need to then get really robust lane detection market.
Yeah.
Working well for this method to work. So you're pushing more emphasis on the front end, right? You're lightening up the back end because of the number of features you can use in it less. If you talk to Mike Smart, there's a lot of difficulties getting good lane marking detection. So.
But then again, because those lanes could be sometimes very nicely done, and some other area of the ring road could be very faint. You could still use that. Okay, this is where the area where it's faint. So you know what to do with it. Okay, so
It's like hard coding. I mean, you actually say, we know I'm using something to do it.
no, I know, but I'm just talking about driving our like all of those autonomous cars are driving some geofenced area, right? So they know exactly which route they are going. Nobody's going anywhere.
If you were on a different subject, somebody told me over the weekend that close by Ontario, a town was bidding to be
Strasbourg.
Yeah.
Yeah, we have our tester there.
So the short range.
No, that's okay. Yeah, Strasbourg is doing it. So. Okay, yeah, good. That's just my comment of the outsider, right?
Oh, cool. There should be more answer. Yeah, it needs to be.
Right. See you guys. Thanks.
That's it, man.
Yeah.